Hey guys, this is Yoru. In the last lecture, we have learned how to derive the constraint equations of the slider crank mechanism and how to analyze its displacement. In this lecture, you will learn how to analyze its velocity. In velocity analysis, our goal is to determine the velocity vector q dot, which consists of 4x dots, 4y dots, and 4 theta dots. Now let's review the constraint equations we derived in the last lecture. We have 12 constraints in total. 3 are from ground, 6 are from revolute joint, 2 are from translational joint, and 1 is from driving link. Since by kinematics, as mentioned in previous lecture, we know that if we differentiate the displacement with respect to time, we can obtain velocity. So here we differentiate the constraint equations with respect to time. We can get 12 equations. By solving these equations, we can determine the 12 unknown velocities, which is our goal in velocity analysis. Note that in displacement analysis, we already solved all the thetas. Therefore, the thetas in the equations are known numbers. That's why we need to do the displacement analysis first. Otherwise, we won't be able to solve these 12 equations. But how can we solve them? They are clearly too hard to solve by hand, so we will rely on computers. To do that, we need to convert them into a matrix. Now I'm going to show you how to do that. First, we move everything which is not related to x dots, y dots, or theta dots to the right-hand side of the equation. For example, the omega 1 init and alpha t are not related to neither x dot, y dot, nor theta dot, so we move them to the right-hand side. After this step, you will have 12 equations like this. Then we express these 12 equations with matrices and vectors. We can get a large matrix times the vector q dot equals to another vector. Note that for the large matrix here, we have a special name for it. It is called Jacobian matrix, denoted by J or phi q. This matrix is very important because it will be used in both acceleration and dynamic analysis. As for the vector on the right-hand side, we call it beta, just for convenience. So now we can have the equations jq dot equals to beta. And then we solve for q dot simply by taking the inverse of j. Great! Now we are able to determine the q dot. For the case that driving link is rigid body 3, you can see that the Jacobian matrix and beta here are a little bit different at the 12th row. However, the solving procedure is still the same. We have jq dot equals to beta, and then we solve for q dot simply by taking the inverse of j. Now the only problem here is that how can we get the inverse of j? It is impossible for us to derive the inverse of a 12 times 12 matrix by hand. But don't worry, by using MATLAB, we can easily find the inverse of a Jacobian matrix. So this is the end of this lecture. In the next lecture, you will learn how to analyze the acceleration of the mechanism. See you next time.